Hello, everyone. Thanks for joining. Today, I'm going to present my work titled as XC, Exploring Quantitative Use Cases for Explanations in 3D Object Detection. And this is the outline for my presentation. I will first talk about some background information, and then I will move on to motivation and overview of our contributions. And then I will talk about related work and our proposed method, explanation concentration. And then I will move on to our results for the experiments, and I will end with some conclusions. So let's first talk about some background information. The goal for Explainable AI, or XAI, is to uncover deep model reasoning. And the existing solutions can be categorized into three following types. One is called surrogate model. That is when you use a separate model to explain the black box model. And the other one is perturbation analysis. So you perturb the input and observe changes in the output. And you use these changes as your explanation. And lastly, we have gradients. That means we use the partial derivative of output with model output with respect to model input as explanation. And the gradient-based methods are going to be our focus. When the input is in the form of image, the gradient-based explanations, they are usually in the form of attribution maps, and we'll explain what that means. Here we present an example of an input image with a cat and a dog in it. And we are generating explanations for why the model would classify the image as a dog. And we can see that from both of the explanations we're showing, the face of the dog has been highlighted. So this means that the facial feature of the dog is heavily influencing the model output. And it makes perfect sense, right? Because we're explaining the classification result for a dog. And the positive attribution would mean the corresponding feature is positively influencing the model output. And in this case, that would mean the feature is increasing the model's confidence that the image indeed contains a dog. Negative attribution would be the opposite, right? Reducing the model's confidence in that. And the magnitude of the attribution values will correspond to the degree of influence of the corresponding input features. Okay, now I'm going to talk about our motivations. So as you can already see, for these sort of explanations, we need human observers to extract insights from them. And it's not really scalable if we are dealing with very large data set. You cannot expect a human to go through every single image and inspect their visual explanations one by one. So it would be nice to have some sort of quantitative measures based on the explanations, which can allow automatic decision makings later on without human labor. And another motivation is the lack of research in XAI applied to object detection. So it would be nice to fill in this gap as well. Okay, and here's the overview for our contribution. We propose a new quantitative measure based on the explanations. We call it explanation concentration. It measures the concentration of attributions within each predicted bounding box. And we also discovered that XC can distinguish true positive and false positive object predictions effectively. And then we also use XC and another attribution-based quantitative measure called pixel attribution prior to improve the object detector performance. Now we are ready to talk about the related work. In my thesis, I present a more detailed literature survey, but here I'm only going to talk about the most relevant work. So first, I'm going to talk about a gradient-based explanation method called integrated gradients. So the simplest gradient-based method would be just simply using backpropagation to obtain the gradient of the model output with respect to input features. But integrated gradients does a few more extra steps to ensure some desirable properties of the end result. The end result being the attribution map generated as a visual explanation. So one desirable property of IG is sensitivity. It means that the influential features are guaranteed to have non-zero attributions assigned to them, and features with no influence on model output are guaranteed to have zero attributions. And this property would make the attribution map very visually appealing to human observers, and it will generally make more sense. So here is one example. We have an input image of a camera which has been labeled as reflex camera by the image classifier, and then we ask integrated gradients to explain this prediction, right? Why is the image classified as camera? And IG correctly identified the key features of the camera. However, if we just use the gradients obtained by backpropagation, you can see that the gradients the end result is not very clear, right? You cannot see the key features of the camera very well. Now let's talk about pixel attribution prior, which is one loss term, which was one quantitative measure based on explanation. And it has been used as a loss term to punish differences in attribution values for neighboring pixels. Why would that be interesting? Well, if we can force the model to focus on learning from patches of pixels rather than focusing on individual pixels separately, then we can make the model more robust to small perturbations in pixel values. And here we show some example, right? Say the original image is digit 7, and then we have a model trained without PAP loss, and then we generate the attribution map for this specific input. We can see the attribution map is very noisy, indicating that individual pixel values are having quite big influence on the model output. However, when we train the model with pixel attribution prior, you can see the attribution map is now very smooth. This indicates that the model is right now focusing on groups of pixels rather than individual ones. And the original authors, they have claimed that they were able to use PAP to improve model robustness against noise in MNIST and CIFAR-10 data. Okay, now I'm going to talk about point pillars, which is the object detector we are using for our experiments. It's a 3-stage network. The first stage is called a pillar feature net. So what it does is it converts a 3D point cloud into a 2D representation. And how it does that is it splits the 3D point cloud into a number of pillars. And for each pillar, it learns a certain number of features. So the number of pixels in the pseudo image, the 2D representation, is the same as the number of pillars assigned to the 3D point cloud. And the number of channels within each pixel is the same as the number of features assigned to the points we learned in each pillar. And then we feed the pseudo image through a 2D CNN backbone network to learn more features. And we feed the result of that into our detection head. In this case, it's a single shot detector, and then it will produce the end bounding box predictions, the box parameters and the class scores and so on. All right, now let's talk about our proposed method, explanation concentration. This is an overview of our pipeline. You can see it as a 2-stage process. So in the first stage, we feed the point cloud into the point pillars network, and then we will get a certain number of predictions as the end result. And in the second stage, we select particular predictions that we wish to explain, and then we pick the pseudo image as the input for the explanation method. Why do we do that? Why don't we just use the point cloud as the input Well, these explanation methods has been designed and tested for 2D image inputs. So it will be more convenient to just apply it to the pseudo image, which is, well, a 2D representation of the 3D point cloud, right? Then we don't need to worry about, oh, if we apply to point cloud, will this method still work or not? Okay, with that explained, I just need to make one more clarification. So far, we have only explored generating explanations for the class scores. We have not generated explanations for the bounding box parameters. All right, so here is just one example for the attribution map generated for a car prediction. So you can see in the original point cloud, we have a car object highlighted by the blue box. And then, yeah, we feed it into point pillars. We learn a pseudo image, and then we generate the box prediction. It's highlighted by the red box here. And as you can see, we can generate both positive and negative attributions. But here is one very interesting observation, right? We can see that sometimes the features outside of the bounding box can influence the model's decision on this particular prediction as well, right? So this leads us to our proposed method, XC, which quantifies the concentration of the attributions within the bounding boxes, right? So we can do that in two ways, either by summing and by counting. So let's look at by summing first, right? Let's look at the first three equations. The very first one, we have this symbol lowercase s, which represents the sum of attribution values within the predicted bounding box and also exceeding a certain threshold. Why do we use a threshold? Because we want to filter out insignificant, noisy attributions, right? So we do the summing process for the attribution values within the predicted bounding box, and we call it the lowercase s. And the uppercase s is pretty much the same thing, but this time we are not limiting us to the predicted bounding box, right? We're doing it throughout the entire pseudo image. So now we have it, the concentration of attribution by summing. We label it as XCS. And the superscript plus just means we are analyzing the positive attributions. We can have a similar metric for a similar score for the negative attributions as well. And now let's look at the next three equations, right? Computing XC by counting the attributions. So what we do is we first count the number of pixels within the predicted bounding box that has attribution values exceeding a certain threshold. So this is called the lowercase c, and the uppercase c is we do the counting process again, but this time we're doing it across the entire pseudo image. And then we do a division and we get the concentration of attribution by counting. Okay, so with the XC metrics explained, we can now moving on to the experiments on using XC to classify true positive and false positive object predictions. Here are some implementation details. The most important thing is we have experiments on two different data sets. One is the KITTI data set, the other one is the Waymo data set. So for KITTI, we trained 3 models, and for each model, we generate roughly 67,000 predicted boxes on the validation set. And for each predicted box, we record the XC scores, the class scores, the distance to the sensor, and the number of LiDAR points within the predicted bounding box. As for the Waymo dataset, we have generated about 94K predicted bounding boxes. So let's first look at the distribution of XC values. So these plots here, they are generated from the predictions from the KITTI validation dataset. And then we pick to visualize the distribution of one of the XC scores that we designed. And this XC score is computed based on integrated gradients attributions. And you can observe that the distribution for the TP and FP predictions are very different, especially for the car class. But the distribution is not too different for the pedestrian and cyclist class. Well, still different enough to visually observe, but just not as great. And here, this is pretty much the same thing, but this time we are computing XC based on the attributions obtained by simple backprop. And surprisingly, although IG is a more sophisticated method, somehow we are able to achieve greater distance between the cumulative distribution function of the TP and FP XC scores when we use just backprop compared to IG. This is indicated by the KS distance shown in the plots here. You can see that for pedestrian and cyclists, right now we have a greater KS distance than before. All right, so of course we can't just draw concrete conclusions by looking at the distribution plots. We need to have metrics specifically designed for binary classification tasks. So let's say we just treat the TP predictions as the positive class and the FP predictions as the negative class. And we can apply the following threshold independent metrics. So one of the metrics is called area under the receiver operating characteristic curve. Don't be scared by the name. What it essentially does is it evaluates a score's ability to correctly identify both the positive and negative classes, right? So this particular metric doesn't have an emphasis on either the positive or negative classes. It evaluates them both. And the other metric is called area under the precision recall curve. And this metric does reflect a score's ability to correctly identify the positive class. So this one does have an emphasis. And then we have AUPR OP. So it's AUPR, but now we are treating the FP predictions as the positive class. So this metric will reflect the performance on the FP predictions, on correctly identify the FP predictions more. Okay, and here's our results. Let me just explain. So to compare our XC scores better, we also show the performance of some other scores. For example, the top prediction score, top class score from the predictions, and also the distance of between the prediction and the sensor, and also the number of points within the predicted bounding box, right? Perhaps if a bounding box has more points, it's more likely to be a true positive prediction, something like that. And we also have random guess as a baseline for comparison. We can see that in most cases, for all three different metrics and for all the different object classes, the best performing score is always the top class score. However, the second best performing score is always one of the XC scores, right? As highlighted by bold here. And there's another interesting observation. The XC score obtained by backprop, they almost always outperform XC score generated by IG. And another interesting observation is that the best performing XC scores almost always outperform the number of points and distance to the sensor. So this shows just the value of our XC scores. And then here are the results from the Waymo dataset. Basically tells the same story. Nothing too different from the KITTI results. Okay, so you may ask, since the top class score is already doing so good, why bother exploring the XC score, right? So perhaps if we combine the top class score with XC score somehow, we can get a better score than both of them, right? So to validate this hypothesis, we use a two-layer MLP to generate a new score from multiple input features. So for each model trained on KITTI, we create a new dataset DF from the 67K predictions. And for each prediction, we record the top class score, the predicted label, the 4 XC scores, and so on. And then we apply fivefold cross-validation on the DF dataset when training the MLP. And of course, we are using the true positive versus false positive label as our training label. And then we record the average validation set performance on the new score generated by the MLP. And our results are average over the 3 different models trained on KITTI. So here are our results. We can see quite significant improvement when we add the XC features in addition to the top class score, especially for the pedestrian objects. You can see, especially for the AUPR metric, we get quite a bit of improvement. But the improvement is less for the car and cyclist class. And also we can see that when the number of points in the predicted box is less than 100, that indicates there's a lack of information within the predicted bounding box. The improvements seem to be more significant. Okay, now we are going to talk about improving object detector performance using XC and PAP. So when designing loss function based on attributions, there's one big problem. Computing attributions for all predictions during training is just way too time-consuming to be realistic. So we would pick a small subset of predictions, we call it P, and then we design loss functions based on the attributions for the predictions in P. We explore 3 different objectives. One is to increase XC, the other one is to reduce XC, and the other one is to reduce PAP. Note that the attribution-based loss functions are used in conjunction with the regular loss functions, the classification and the regression losses. So this is the loss function for increasing XC, right? So J here is the index for a particular prediction, and I here is the index for a particular frame. So we can sum up the prediction-wise losses to get a frame-wise loss, lowercase psi, and then we average this frame-wise loss psi over the training batch B, right? And then we multiply this average by a weighting factor lambda. The lambda weighting factor needs to be chosen carefully so that it's significant enough to influence the training process, but it's not large enough to overwhelm the regular losses. And this is the loss function for reducing XC. So rather than doing 1 minus XC as we did before, here we just use XC directly, so that greater the XC value, the greater the loss. And here we are showing the loss function for reducing PAP, right? So I show the equation for PAP at the very top, where the Greek letter phi indicates the attribution value, M and N indicate the pixel coordinate in the attribution map. So you can see PAP is indeed punishing differences for neighboring pixels. All right, and then we again get a frame-wise loss, omega, averaged over the training batch, and then multiply by a weighting factor. Okay, now let's discuss some training strategies that we explored. Right, we explored one strategy, we call it XC top 3 increase. This is to increase XC values for the high confidence predictions. And then XC bottom 3 reduce, this is to reduce XC for the low confidence predictions. And then we have XC bottom 3 increase, this is to increase XC for the low confidence predictions. And then lastly, we have XC random TPFP. This is to increase the XC values for the TP predictions, and then reduce XC values for the FP predictions. And then here are just some implementation details for your information. And then due to time limit, we only explored one XC score. We didn't explore all 4 of them. And we had only used XC based on backprop attributions. And this is the learning rate that we are using. We're using OpenPC, that's default learning rate scheduler for add-in optimizer. You can see we start with a small learning rate, gradually go up and then reduce. Okay, and here's the result. Don't be too overwhelmed by all the numbers here. The key values here are just the one labeled as regular. So this is the result when we train the model without any losses based on attribution values. So this is just the regular training setting. And then we show the performance of the different strategies at different epochs, right? So we show the performance at the end of the 20th, 40th, 60th, and 80th epochs. And the metrics presented here are average precision, R40. R40 meaning the average precision values are averaged over 40 different recall values. Okay, and then we use underline to indicate less than 1% improvements compared to regular training, and then bold to indicate more than 1% improvement compared to regular training. And we can see that at the 20th epoch, XC bottom 3 reduced. That is to reduce the XC values for the low confidence predictions. This particular strategy led to quite a bit of improvement at the 20th epoch, and also led to some improvement at the 60th epoch as well. So I would say this strategy is certainly worth exploring further. However, all the other strategies fail to significantly outperform the baseline. And we also explored training with PAP. So we have two strategies here. One is called PAP bottom 3. This is to reduce the PAP values for the low confidence predictions. And we have PAP top 3. It's to reduce PAP values for the the highest confidence predictions. And we had explored both positive and negative attributions, some implementation details for your information, and also learning rate is the same as before. Now let's look at the results. Now you can see we have a lot more bold and underline. So that means training with PAP in general gives better performance than training with XC. I guess it's understandable because object detection is a very complicated task, and then improving model robustness using PAP can certainly help. The one performed the best, I would say, is the PAP negative top 3. So that's reducing the PAP values for the top confidence predictions based on the negative attribution values. And then we have some comments, right? One very noteworthy observation is that we seem to have the most improvements at the early epochs, right? At epoch 20. So this is hinting that perhaps when training, so you can think of it like this. At the 20th epoch, we only see the data set 20 times, right? So this is indicating that perhaps training with attribution may allow greater data efficiency, meaning that we can achieve the same performance with less data seen by the model. Although it might be more computationally expensive, but we can save the data, right? So it's still very valuable. And also the increase in learning rate in the middle of the training cycle. Let's go back to this part, right? Perhaps the increase of the learning rate at the middle of the training cycle might be the reason why we are getting such bad performance at the 40th epoch in the middle of the training cycle. So to get better results, further tuning might be required. Now we're ready to talk about some conclusions. So as we can see, we already proved that XC scores can distinguishing TP and FP predictions quite effectively. So this achieves our original goal, right? We said that we want to allow automatic decision making from some metrics generated from the attributions, right? So that will save human labor. We don't need to dive in and then look at every single attribution map. And also, when used quantitatively, simpler XAI methods such as backprop may offer greater values than the more complicated ones. And yeah, training object detector with loss functions based on attribution values is a promising direction, and especially from the data efficiency point of view, as discussed just now. As for future work, we had only explored one object detector, which is point pillars. But it would be nice to see if the benefit offered by XC or PAP is present for other object detectors as well. And of course, we could explore more XAI methods too. And of course, more extensive exploration is required for the training object detector with XC and PAP. We had only gathered some early results. We don't think we can draw very concrete conclusions yet. And that ends my presentation. Now it's time for questions.